Remember that we are here in the middle of our kinetics unit, and kinetics is the study of reaction rates, how quickly reactions progress, how they proceed. We spent all last video talking about that, talking about rate laws, the differential rate law. Remember, the differential rate law will always have this form where it relates the rate of a reaction to the concentration of the reactants. Right now, you should understand several things. You should understand how to use data of initial concentrations and initial rate, how to manipulate that data to write a rate law for a reaction. We can use this data to experimentally determine these exponents. These exponents are the order of the reaction with respect to that reactant. If we add the exponents up, we get the overall order of the entire reaction. And you should know how to find K experimentally using the data, and how to find the units of K. That's going to be really important. And we'll go over that a little bit more today. And remember that a differential rate law relates the rate of the reaction in units of concentration per time. How is the concentration changing per time? It relates the rate to the concentration. We've already thought through the idea that as concentration changes, the rate changes. As concentration, for example, of my reactant NO2 here goes down, you can see that the slope of this curve gets shallower and shallower. The reaction is slowing down as time goes on because the concentration of NO2 is dropping as time goes on. So it just makes sense that rates, how quickly the reaction is progressing, of course it's going to depend on how much stuff you have available to react. We talked about that in the last video. Remember that we have two different types of rate laws, the differential form, and today we're going to talk about the integrated form. Remember, the differential rate law relates the rate to the concentration of reactant. Here, the integrated rate law is going to express how a reactant concentration depends on time. So we're trying to relate concentration and time. This is a much more helpful form of the rate law because we can actually measure these. It's very, very easy for us in the lab setting. Hopefully we'll be able to do this. To measure concentration of a reactant as time goes on. So these forms of the rate law, the integrated forms, are much simpler. Listen, this is all going to be about pattern recognition and about knowing how to create a good graph. So you need to be ready to take some notes, work some example problems. You need to have your graphing calculator. You need to watch and listen very carefully. We're going to walk through 3 different versions of the integrated rate law. And to make it simple, we're going to look at reactions that only have one reactant. That will always be true. The College Board for the AP exam, you do not have to know how to do this for reactions with more than one reactant. You may have to in some special cases, but I will help you with that. Okay, so let's first look at a first order reaction. Remember what that means. That means that in our differential law, the exponent up here would be a 1, so I've left it out. A first order reaction with respect to our one reactant. You know the differential rate law would look like this. And now you need to memorize that the integrated rate law looks like this. This is only true for first order reactions with one reactant. Let me talk to you about what all of this means. Ln, of course, is natural log. That's the natural log function on your calculator. Whenever you see something in brackets, that's concentration. So this is the natural log of concentration of the reactant. Our reactant is called A. And this is the concentration at some specific time, and it's changing as time goes on. So the natural log of the concentration at some specific time will be equal to negative K. K is the exact same rate constant that we have in our differential law, times T, where T is time, plus the natural log of the concentration of the reactant. That little 0 down there means at time 0, so initially. This equation should look familiar to you. It follows this form, y equals mx plus b. It is a linear equation. All of our integrated rate laws are going to be linear. So my y variable, my output variable, my dependent variable is the natural log of concentration. My input variable, my independent variable, my x variable is going to be time. The slope is going to be negative k. And the y-intercept will, of course, be the natural log of my concentration at time 0. What was my concentration at time 0? Take the natural log of that. That will be the y-intercept. We're going to look at an example of this later, and I have plenty of pictures and graphs to show you. But you need to understand that this follows y equals mx plus b form. Here's my y variable. Here's my slope times x. Here's my y-intercept, okay? So you are looking at a first-order reaction if the natural log of concentration graphed as the y variable with time as the x variable, if that forms a straight line, the reaction has got to be first order. This is a question that the College Board loves to ask in multiple choice and free response. If you are able to graph natural log of concentration versus time, and that graph makes a straight line, the reaction has got to be first order. We can also express this as a ratio. If you know some things about log math, what we can do is add kt to this side, subtract away natural log of a from both sides. And whenever you have a natural log minus another natural log, you can put them over each other like this. You don't really need to worry about that. Okay, here's some more information I'm going to throw at you. Half-life. We need to talk about what that means. Half-life has this abbreviation, T with a subscript 1/2. A half-life is the amount of time required for the concentration to drop by half. How much time does it take for the concentration to get cut in half? That is what this equation means. So if we have some concentration at some time later, the reaction is progressing. My concentration of A is decreasing because it's a reactant. It's getting consumed away in the reaction. At some point in time, my concentration is going to reach half of what it normally was. The concentration is now half of the original value. The half-life is the amount of time required for that to happen. How much time did it take for the concentration, for the amount of that reactant to get cut in half? You need to know that for first-order reactions, and only for first-order reactions, the half-life is equal to this, 0.693 over K. This is interesting, and you need to commit this to memory as well. These can get you really quick and easy points on the AP exam, and I'll talk to you about why this is true in a little bit. For first-order reactions, these two statements are true only for first-order reactions. Notice I'm talking about first-order reactions. For first-order reactions, the half-life is 0.693 over K. Notice that only depends on K. It only depends on the rate constant K. For the first order reaction. It does not depend at all on what the concentration actually is at that time. So we're going to see later that for other types of reactions, second order, zero order, the half-life is going to have a different pattern. Remember, this is all pattern recognition. So if your half-life is not changing, if the half-life is constant, a constant value, 0.693 divided by K, the reaction has to be first order. This is another way to test for whether or not a reaction is first order. You can look at what the half-life is doing. If the half-life is constant, if it does not depend on the concentration, it's got to be a first order reaction. This is a graph of what a first order reaction would look like. Here I have time and concentration data, and you can see my initial concentration at time 0 is 0.2 molar. And you can see that it takes about 7 seconds for that concentration to get cut in half, 0.2 to 0.1. So I would say my half-life is 7 seconds. How much time does it take for the concentration to get cut in half again, to go from 0.1 to 0.05? Well, it takes another 7 seconds. To get cut in half again from 0.05 to 0.025, it takes the exact same amount of time. So I can imagine a question where you are given concentration versus time data, and you're asked, based on this data, based on this graph, is the reaction first order, second order, zero order? You can look at this graph and know right away that this reaction is a first order reaction because the half-life is constant. It's always 7 seconds. Later we will see that for zero order, second order reactions, the half-life is going to change as time goes on. First order reactions are the only reactions for which the half-life is constant. The half-life is not changing. Okay, and notice that we could actually calculate the value of k for this reaction, the rate constant. If we rearrange this equation to solve for k, 0.693 divided by the half-life would give me k. The half-life here is 7 seconds. So if I divide 0.693 divided by the half-life of 7, rearrange this equation, I'll get my k value. So that's one way that you can find the rate constant k for your reaction. Okay, so let's say that we have concentration versus time data, like we just did. What I'm telling you about a first order reaction is that the natural log of concentration versus time will give you a straight line. Remember, first order reactions have this version of the integrated rate law. The natural log of concentration versus time yields a straight line, and that's exactly what we see here, whose slope is the negative value of the reaction constant K. Okay, you need to commit this to memory. This may make more sense for you whenever we actually do an example problem here in a little bit, but in order for us to do an example problem, I have to go through each of the order types. So right now you need to understand what is true for the integrated rate law for a first order reaction. It's true that the natural log of concentration versus time yields a straight line whose slope is negative k and whose y-intercept is the natural log of the initial concentration. You need to understand that the half-life is constant. The half-life does not change for a first order reaction. Let's proceed to a second order reaction. You know the differential law for this would have a 2 up here. And remember, we're only looking at reactions that have one reactant. A is my reactant. So this is second order. If I were to write the differential rate law, it's going to look like this now. Excuse me. If I write the integrated rate law, it's going to look like this now. For first order, it was the natural log of the concentration versus time that yielded a straight line. For second order, commit this to memory, it's going to be 1 over the concentration data versus time that yields a straight line. Once again, this is y equals mx plus b. My y-dependent output values are 1 over the concentration, the inverse of concentration. My slope is positive k this time. Last time it was negative k. This time it's positive k. There's my x value, my x variable, y equals m times x, and then here, of course, is my y-intercept, 1 over the original concentration at time 0. For first order, it was the natural log of the concentration versus time that created a straight line. For second order, it is 1 over the concentration versus time that will create a straight line, whose slope is not negative k, but k. All right, let's talk about half-lives. You need to understand that the half-life for second order reactions is going to get longer as time goes on. It takes more and more time for the concentration to get cut in half as time goes on. We can see that that's true because the equation for half-life here has concentration on the bottom. And that concentration with the 0 right there, that 0 is referring to the concentration at the beginning of that half-life period. I'll explain that in a second. You don't really need to understand this equation, you need to know it conceptually. For a second order reaction, each successive half-life is double the preceding one. Half-lives get longer as time progresses, okay? Because this concentration down here is going to be getting smaller, so I'm dividing 1 by a smaller and smaller number. My half-life gets bigger and bigger. 2 key things for second order reactions. The integrated rate law is a linear relationship between 1 over concentration versus time data, and the half-life for the reaction gets longer and longer. Remember, for first order, the half-life was constant. So I can imagine, once again, a question where you're given concentration versus time data, and you can find the half-lives quite easily. Here, I start with 0.2 moles per liter. That's the concentration of my reactant at time 0. The half-life is how much time it takes for that to get cut in half. So dropping down to 0.1, that has taken 1 to about 2.5 seconds. And now I want to know what the second half-life is. Well, I cut this in half again from 0.1 down to 0.05. And you can see that now the half-life is about 5 seconds to cut it in half. The third half-life, going from 0.05 to half that. Remember, half-life is the amount of time required to drop the concentration by 2 to cut it in half. So now the time required to cut it in half is getting longer. So just by looking at this graph, I can see that my half-lives are lengthening. That is only true for a second-order reaction. All right. So here I have concentration data versus time. And you can see that 1 over the concentration data is yielding a straight line. That is only true for second order reactions. All right, 0 or 0th order reactions. You know the differential rate law for this is just R equals K. Because if I put the concentration of A and I raise that to the 0 power, the order on it is 0. Anything raised to 0 power is 1, so that drops out of my equation. The rate is equal to K. This is the simplest. Concentration versus time data will already be linear. I don't have to manipulate it at all. I don't need to take the natural log. I don't need to take 1 over. If concentration versus time data is already linear, y equals mx plus b, it's got to be a 0th order reaction. So concentration versus time will create a linear function with a slope of negative k. Okay, so let me get rid of this real quick. Okay, so now let's look at what the half-life is like. The half-life has concentration over 2k, and again, where that little 0 there means at the beginning of that half-life, not necessarily at the beginning of the whole reaction. So you can see that as time goes on, my concentration is going to be decreasing. So the half-life will be decreasing. This is only true for 0-order reactions. Each successive half-life is half the preceding one. Each successive half-life is getting shorter and shorter. I'll go back to that. Okay, so here's a differential rate law graph for a 0-order reaction. Remember, the differential law relates rate and time. The differential law for a 0-order reaction is just R equals K. So the rate is a constant K as time goes on. For the integrated law, the concentration versus time data is linear with a slope of negative K. Okay, so if we analyze this, for half-lives, it makes perfect sense that the half-life now gets shorter for 0-order reactions. Here's a graph of a 0-order reaction, concentration versus time. And you can see that initially to cut it in half, it takes 1, 2, 3, 4, 5, 6, about 6.5 seconds to go from 0.2 to 0.1. To cut it in half again is going to take a shorter amount of time, half of the first half-life. To cut it in half again from 0.05 to 0.025 to find my third half-life, my third halving of concentration takes an even shorter time. So each successive half-life, going from first half-life to second, second to third, where again, half-life is the time required to cut the concentration in half. Again, each successive half-life is decreasing, it's getting cut in half. Okay, so that is only true for a 0-order reaction. It's important that you understand what conditions, there are specific conditions that give rise to 0-order reactions. If there's a catalyst, typically the reaction will be 0-order. You guys don't know what a catalyst is yet, but we're going to talk about that later. If the catalyst is an enzyme, that's a biological catalyst. You guys should learn about that in biology. Then it's probably going to be a 0-order reaction. This one's really important. Let's say that we are actually doing a reaction where we have more than one reactant. Everything I've been talking to you about today, remember, is from the perspective of a reaction that just has one reactant. Maybe something is decomposing. But if we do have 2 or more reactants, it is possible for one of those reactants to behave like the reaction is 0-order with respect to that reactant. For example, let's say that I'm looking at the reaction A plus B yields C plus D, and I'm trying to study it in the lab or something. Well, because I have 2 reactants, it's going to be really difficult for me to figure out the order on each reactant. So what I can do is set up the experiment such that the concentration of B is much, much greater than the concentration of A. right when I start the reaction. And again, we're actually going to do this in the lab. And if I do that, as time goes on, because my concentration of B at the beginning was so much bigger than A, it is as if the concentration of B doesn't even change. That concentration of B was so large that while A is so small, all of it gets consumed, and A experiences significant change because I started with so little of it. B is not going to change a lot at all. So I'm almost like forcing the experiment, I'm forcing the reaction to act like it is zero order with respect to B. So I can, whenever I'm doing my equations and my experiments, I can actually ignore B almost and just find the order on A. And then if I wanted to find the true order of B, I have forced it to be zero order. It's probably not really zero order. I can go back and flip this scenario so that B is changing. So if I make the concentration of one much greater than that of the other reactant, then I'm forcing the system to behave as if that reactant, the one that's present in greater concentration, is zero order for that reactant. We'll talk more about that later. Okay, so things to remember to summarize all of that. For first order reactions with one reactant, the integrated rate law will be this. The natural log of concentration versus time will give you a straight line with a slope of negative k. The half-life is constant. For a second order reaction, the integrated rate law 1 over the concentration data as time goes on will give you a straight line with k as the slope, and these half-lives get longer as time goes on. For zeroth order, the concentration versus time data is already linear, don't have to manipulate concentration at all, and the slope of that is negative k, and these half-lives get shorter. Okay, so let's see how we would use all this information actually to solve a problem. So first I'm going to give you a problem-solving strategy, and then we're actually going to solve a problem. You may pause the video to write this down. It's kind of long, but it should be pretty intuitive. I'm going to go through this quickly, and then we're going to solve a problem together. I have 2 example problems for us. So we want to know what the integrated rate law for a reaction is. So we're given a reaction. We're always going to be given time and concentration data, and we want to write the integrated rate law. So what we can do is first we can see if the half-lives give us any information. See if from the time and concentration data we can pick out the half-lives. How much time does it take for the reactant to get cut in half and then get cut in half again and again? If the time required for the concentration to get cut in half, if the half-life is constant, it's got to be first order. Boom, we're done. If the half-life is lengthening, it's got to be second order. If the half-life is shortening, it's got to be zeroth order. So we're going to look at our data and see if we can determine something about the half-life. If we cannot, we've got to go on to step 3, which is more complicated. So if we cannot easily determine the order by analyzing half-lives, we've got to use a graphing calculator to plot the data. So what we're going to do is create 4 lists in our graphing calculator. So if you have a TI, that's stat edit, and that lets you edit your lists. In list 1, you're going to be putting time data. In list 2, you're going to be plugging in the concentration data that corresponds with that time. In list 3, you're going to take the natural log of list 2. You're going to take the natural log of that concentration data. You don't have to plug in those values one by one. You can actually go to the top of list 3 and say list 3 equals the natural log of list 2, and it will generate all the values for you. You don't have to go in and type natural log of this, natural log of this, natural log of this. So you're going to put in natural log of concentration data in list 3, and then you're going to put 1 over concentration data in list 4. I hope you can see what we're doing. We're going to create 3 linear regressions and see which one is a straight line. So we're going to run linear regressions. You go to stat, calc, linreg, and here's the goal. We are trying to see which data set is linear, which one creates the best line of best fit. Remember that whenever you do a linreg, we should be getting R values, R and R squared. The closer those are to 1, the better the data fits a line. So what we're going to do is create 3 different linear regressions. For each of them, we're going to have L1 be the x variable. Remember, time data is L1. In our first, second, and zero order integrated rate laws, time is always the x input independent variable. And then our y variables will be list 2, another one with list 3, and another one with list 4. So we're running these 3 different linear regressions, list 1 versus list 2, list 1 versus list 3, list 1 versus list 4. We are just taking our time and trying to fit it into a line, into a linear equation with concentration, natural log of concentration, 1 over concentration. Whichever one of those makes the best line, we know what the rate law is. We know what order the reaction is on that reactant. So whichever one makes the best line, whichever one has the best R values, the R value is closest to 1, or you can actually go into your stat plot and look at the data plotted. Then we can see what the order of the reaction is. For example, if time versus concentration, list 1 versus list 2, creates the best line, the reaction's got to be zero order because that's true for zero order reactions. Time versus concentration data makes a line. If time versus the natural log of concentration, L1 and L3, makes the best line, then the reaction has to be first order. If time versus 1 over concentration, L1 versus L4, makes the best line, the reaction has to be second order. So that's going to show us, that's going to help us see what the order of our reaction is. And then we can use the equation our linear regression made to find the K value. Remember that the K value is the slope. For zero and first order reactions, the slope of the line will be negative K. So if it gives you a slope of negative 5, you know your K value is 5. For second order reactions, the slope of the line is already K. All right, so our problem solving strategy, first we want to see from the time and concentration data if we can determine something using the half-lives. If we cannot, we have to do this linear regression thing where we see if time and concentration makes the best line, then it's zero order. If time and natural log of concentration makes the best line, it's first order. If time and 1 over concentration makes the best line, it's second order. And then we can grab the slope from the linear regression to figure out what the K value is. Okay? Oh, all right, so let's do an example problem. So we want to write an integrated rate law for this reaction. I only have one reactant, and you can see here I have time and concentration data. So the first thing I want to do is try to determine if the half-lives tell me anything. And I don't have like half-lives immediately evident. I know I start with a concentration of 1. So my half-life would be when that drops to 0.5. I don't have that data. I know it's somewhere in here. So the half-life has got to be in here somewhere. But I don't know for sure. So 0.5 is in here somewhere. And then the second half-life would be somewhere between here, going from 0.5 to 0.25. So I really don't know much about the half-lives. I can kind of guess. We can try to guess that the first half-life is going to be somewhere in between this, going from 1 to 0.5. Maybe, let's see, what's between that? Maybe like 900, 800, 900 seconds. And then you can see that about 900 seconds later, I've dropped by half again. So it seems like the half-life will be constant. So maybe I'm guessing this is first order, but I don't really know for sure. Okay, so what I'm going to try to do now, because the half-life thing did not really help me, I mean, I can kind of guess that it's going to be first order, is I want to try to make graphs of time concentration, time natural log of concentration, and time 1 over concentration. So you can do this on your calculator given the instructions I gave you earlier. I can't show you that on this screen, so what I'm going to do is go to a graphing website called desmos.com. So Desmos looks just like this, desmos.com. Whenever you go there, you will see a screen that looks just like this. And what I want to do is put my data into Desmos. The best way to do this, though, is to first make a spreadsheet of the data. So I just copy the data down into a Google Sheet. So here you can see I have time, concentration data, And what other two things do I need to check? I need to check natural log of concentration data. So I'm just going to type equals ln of B1, hit enter. I can copy that, paste it down the whole column, and now I have natural log values of each of those expressions. And then what does this column need to be? It needs to be 1 over, so I'm going to say equals 1 divided by parentheses B1, enter. I'm going to copy all of that down. And now you can see that I have time, concentration, natural log of concentration, 1 over concentration. All right? And these are the things I want to check. So now I have my data fleshed out. I can copy this whole thing and paste it into Desmos. Okay, so now it has time data. Y1 would be concentration data. Z1 would be natural log of concentration. And U1 would be what it's calling my 1 over concentration. So what I can do is now try to run some tests. So Y1, this is where you would run a linear regression in your calculator. So this would be my dependent variable, list 2 here for you would be the concentration data. I'm going to say, hey Desmos, tell me, is it proportional to, in other words, does it fit some linear regression to a slope times my time data plus a y-intercept? And you can see that my R values here are kind of crappy. So that is not going to be a great regression for me. I'm thinking that this is probably not a time and concentration would be 0 order. I'm thinking it's not a 0 order reaction. So what I can do now is go down to my next section and say, hey, what about this natural log data? What about Z1? Is it proportional to a slope times x1 plus b? And remember, this was our guess that it's probably going to be first order. This is natural log data, natural log versus time data. If that's aligned, it's going to be first order. And you can see those are excellent R values. I'm thinking those are very, very good. So maybe I should hang on to this. Maybe it's going to be first order. I do want to go ahead and check my, my second order, though. Time, concentration, natural log of concentration. U1 over here is my 1 over concentration data. So I'm going to try that. Hey Desmos, is U1 proportional to a slope times my x1 data plus a y-intercept? And you can see there that I get some R values, but they are not as good at all. So what I've done is I've made lists. I've run a linear regression of time with each list. Time and concentration, that's me checking the hypothesis that it's 0 order. I can reject that hypothesis because this is not a good line. Natural log of concentration versus time, that's a great line. So I'm thinking it's probably first order. 1 over concentration times time, that's a crappy line. So I'm going to get rid of that. So I've just determined that this is a first order reaction. And I know that my slope is this value right down here, that m value. So I know it's first order because the natural log of concentration versus time yielded the best straight line. And I can write the expression for that. The natural log of H2O2 concentration is going to be equal to K, negative K, where that was, according to Desmos, 0.000839 times time plus the natural log of my initial concentration, H2O2, with a subscript of 0 to say that's initial at time 0. So this is my first order rate law for this chemical reaction. Yay. So I could also write the differential rate law. This is the integrated rate law. I could also write the differential rate law, the form that has R equals K times the concentration of my reactant. My reaction is H2O2 times to the power of some exponent n. Well, we've determined what the exponent is, haven't we? We've said that it's a first order reaction because the natural log of concentration versus time was a straight line. So I know that n here is 1. My exponent up there is a 1. I don't have to write it. And I know what k is. K is the negative value of this slope. Remember, K is always going to be a positive number. 0.000839. So I now am able to write both of my rate laws, integrated and differential. All right. Now that we've walked through that example, I would like for you guys to do this one. I want you to give me an integrated rate law and a differential rate law for this reaction. Remember that first you're going to see if you can determine anything about the half-life. I don't think you're going to be able to with this data. And then you're going to try to use your graphing calculator to see which plot works best. Time versus concentration, time versus natural log of concentration, or time versus 1 over concentration. I'm going to give you time to do that, and I'll see you in a bit. Okay, so I've gone ahead and put my data in a spreadsheet. I've copied it over to Desmos. This is concentration data. This is natural log data. And what I have over here is 1 over the concentration data. So I'm going to see which one fits. Hey, Desmos, is concentration data proportional to a slope times time plus b? Those are pretty good R values. Let's try the next one. Hey, Desmos, is natural log of concentration proportional to a slope times time plus a y-intercept? Ooh, that's even better R values. Let's see the last one. 1 over the concentration, is that proportional to a slope times x1 plus a y-intercept? Ooh, that's even better. So we have a decision to make. All three of these models fit okay. It looks like my last list, U1 versus time data, makes the best line because that R value is super close to 1. So remember, this is concentration, natural log of concentration, 1 over concentration. And 1 divided by the concentration data here does seem to make the best line for me. So I have just determined that it's second order. This is a second order reaction. 1 divided by the concentration data versus time. If that is linear, then I get a second order reaction. And then here is my slope, and slope for second order is equal to the K value, 0.01417. So I can now write the integrated rate law. 1 divided by the concentration of C4H6 is going to equal my slope, which was 0.0142 times time plus 1 divided by my initial concentration of C4H6. We can say that we know it is second order because 1 over the concentration yielded the best linear regression. And we can also write the differential rate law, can't we? Where R equals K times the concentration of C4H6 raised to some power n. And I know what K is. K is the same constant, so 0.0142. And I know that n is 2 because I've just shown it's a second order reaction because 1 over concentration yielded the best linear regression. So you may be wondering, what's the point of all this? What's the point of taking this data and figuring out what the order of the reaction is? Very important that you understand that we now have a model, we now have a tool, a mathematical device that will allow us to make predictions. We can now plug in any time that we want and predict what 1 over the concentration should be. And that will allow us to figure out what the concentration is at that time. For example, we can say this. Let's say, example, what will the concentration of C4H6b at t equals, let's say 8,500 seconds. So I want to know 8,500 seconds later, what's the concentration going to be? Well, it's this easy, my guys. I can just plug in 8,500 seconds for for time up here, and I can say that 1 over the concentration of C4H6, that's what I'm trying to find. I'm trying to find that concentration is going to be equal to 0.0142 times my time of 8,500 seconds. Again, this rate law is useful because now I can plug in any time and find the concentration, plus 1 over the initial concentration. And the initial concentration I have, I don't actually have the initial concentration, do I? I have the concentration at 195 seconds. So I need to go back to my linear regression and get that initial concentration. I didn't realize that. This first time they give us is not time 0. So this is not my initial concentration. The initial concentration needs to be at time 0. So I actually need to go and grab the B value from this, 59.23. So I know that my y-intercept here is 59.23. Where's that number coming from? That number is coming from my linear regression. Remember, this one is the one that fit the best. And there's my slope, and here's the b. The y-intercept for this is 1 over the initial concentration. So I know that this is equal to 1 over the initial concentration. I could actually solve for the initial concentration if I wanted to from that. Okay, and now all I need to do is just manipulate this, and I get a value of 5.55 times 10 to the negative 3 molarity. So does that answer make sense? It does, because it's less than this. All right, excellent. Let's look at one more example. I want to do one more quick example with you to show you how sometimes you can actually use the half-life idea to figure out what the rate law is. So let's say that we're given this data. I'm not sure what the reaction is. It doesn't really matter. It's probably the decomposition of N2O5. I'm given this data, and oh yay, they've already given me concentration, natural log of concentration, 1 over concentration. So let's say that we want to know what order the reaction is. Is it first order, second order, or 0 order? We know if it's first order, time versus natural log will give a straight line. We know if it's second order, time 1 over concentration will give us a straight line. We know if it's a 0th order, time concentration will give us a straight line. So we could take the time to graph those, run linear regression, see which one works. But there's an easier thing to do, and that's looking at half-lives. So whenever we're looking at half-lives, we just want to look at the concentration data. And remember, half-life is defined as the amount of time it takes for the concentration to get cut in half. So right away I can see that the first half-life is equal to 100 seconds. How do I know that? Because right here, that is a halving. The concentration has gone from 0.1 to 0.05. That is getting cut in half. So my first half-life is 100 seconds. My second half-life, how much time does it take for that to get cut in half again? Well, oh my goodness, look. Right away I can see 0.05, 0.025, that's a halving. How much time did that take? 100 more seconds. So my second half-life is 100 seconds. What about my third half-life? Oh my goodness, 0.025 to 0.0125, that's a halving. That took 100 more seconds. So it seems to me like the half-life is constant. And if my half-life is constant, what does that tell me? That tells me right away that the reaction is first order. So I know it's got to be a first order reaction. In other words, if I did take the time to graph all this crap, time versus concentration, time versus natural log, time versus 1 over, I know that the natural log data would give me a straight line. I figured that out just by looking at the half-lives and remembering that for a first order reaction, the half-life does not change. Okay? So my half-life is 100 seconds. And remember, we have this handy equation for the half-lives for a first order reaction. For a first order reaction, the half-life is equal to 0.693 over K. So I can actually figure out what K is right now. I know that my half-life is 100 seconds. That equals 0.693 over K. Therefore, K equals 0.693 over 100. And therefore, I know that K is 0.00693 or 6.93 times 10 to the negative 1, 2, 3. All right, so now I could write a rate law. I could say that the natural log of the concentration of N2O5 is equal to negative 6.93 times 10 to the third. Remember that for first order and 0th order, your slope is always negative K times time plus the natural log of N2O5 at the beginning. And now I could do this reaction a million times, and I could use this to predict at what time the concentration will be a certain value, etc., etc. What is my differential rate law? You know that for first order, it's R equals K times the concentration of your reactant raised to N. I just found out it's first order because the half-life is constant, so I know that N is equal to 1. And of course, I could plug the exact same K value in right there. So my differential equation is 6.93 times 10 to the negative 3 times my concentration. So using half-lives, it's going to be the simplest thing for you to do if you can get multiple half-lives, if you can figure out things about successive sequential half-lives from your time concentration data. You always want to check that first. It would have been a big waste of time for us to plot all of this because I know that the half-life stayed constant. The half-life was a constant 100, and so I know it had to be first order. And so I can write the integrated rate law, the differential rate law, and then I can use this equation for half-lives of first order reactions to figure out what the K value is. All right. Okay, so what I'm looking at is a file I uploaded on my website. This is a Kinetics cheat sheet, and it has some extra PowerPoint slides printed out in case you guys want to see all this in a different way and see some different examples. It might be a good resource for you. This cheat sheet, you need to study it. You need to have the whole thing memorized. So it goes through what is true about 0 order, first order, and second order reactions. The differential rate law, rate equals something, K in 0th order, rate equals K times concentration to the first power for first order, rate equals K times concentration for this to the second power. And this little delta A over delta T is just reminding you how we define the rate. It's always the rate of consumption of the product. Rate of consumption of the reactant. That's why it's negative. The graphs will look like this, and here are the integrated rate laws. They're rearranged just a little bit, but you can see concentration versus time data is linear. Y equals mx plus b. Your slope is negative k for 0th order. For first order, it's natural log of concentration equals mx plus b. Here's your y-intercept. Negative k for first order is once again the slope. And then for second order, 1 over concentration will equal mx plus b. K is your slope. That's what this is going over. Let's see. I wouldn't worry too much about this relative rate versus concentration. You can just figure that out. You know that for 0th order, the rate does not depend on concentration. So no matter what the concentration is, the rate's got to stay the same. For first order, if you double the concentration, the rate gets doubled because, again, rate is proportional to concentration. If you double the concentration for second order, the rate quadruples because the rate is proportional to the square of concentration. Here are your half-lives For zero order, your half-life is going to be decreasing because concentration decreases as time goes on. For first order, your half-life is constant. For second order, your half-life is getting longer as time goes on. Very important you guys understand that. Finally, here you need to have this memorized, or your math skills need to be good to work it out. You must know the units of the rate constant. For zero order reaction, the rate constant is concentration per time. For first order, the rate constant is 1 over time. For second order, the concentration is molarity to the negative first, seconds to the negative first. You guys must memorize that, and it would probably be, it would probably be good for you to understand different ways of writing this. You guys know concentration is moles per liter, so we could also write this as moles per liter seconds, or we could write it as moles times liters to the negative 1 times seconds to the negative 1. What's another mathematical way of writing this? The rate constant K units for first order, we could just write that as seconds to the negative first. Here we could write this as it's moles to the negative, molarity to the negative 1. That means flip molarity. So that's going to be liters per mole seconds on the bottom. Another way of writing that would be liters times moles to the negative 1 times seconds to the negative 1. So your math skills need to be pretty good to understand those units. If I were you, I'd probably memorize these, but you can figure out what they are based on on how the equations work. Okay? Remember, the point of writing integrated rate laws, it helps you predict what the concentration will be at some time, et cetera, et cetera. One last thing I want to point out to you. In all the examples that we did, I gave you time and concentration data in all of these examples, right? Well, I can imagine a scenario in which the College Board would give you a reaction that involves gases. And instead of giving you, like I have, time and concentration data, maybe they give you time and pressure data or something like that. Maybe your gas is getting consumed in a reaction and turned into a solid. What's going to happen to the pressure in your container as time goes on? It's going to decrease. Remember that our ideal gas law says PV equals nRT, where N is moles. Well, P equals nRT over V. This right here is moles per liter. Pressure is proportional to moles per liter. Pressure is proportional to molarity for gases, as long as the temperature and the volume stay constant. So you need to understand that. If we're looking at a reaction with gases, you might not get time concentration data. You might get time pressure data, but don't let that freak you out. As long as volume and temperature are constant, pressure is proportional to molarity. Pressure is proportional to number of moles to amount. So we can use pressure, if we can measure the pressure of a gas and treat it exactly like we treat all of this. This would be pressure. This would be natural log of pressure. This would be 1 over pressure. We can do the exact same thing. All right? What you guys need to be doing is reviewing these videos, taking good notes, and you need to be working on the practice homework I've given you, the packets. There are really good practice questions. We're still not done with this unit, but if I were you, I would be flipping through those packets, those pages that I've posted on my website to see what problems you are capable of doing. We should have 1 or 2 more videos, and then we'll be done with this unit. And of course, you know that we're going to have a conference call for you guys to ask me questions. I think that's scheduled for Tuesday and or Wednesday. All right, thank you.